All right, welcome to the second video in the Programming Layers of Abstractions series. This is the second video also of the Get Off My Head or GOMF GOM retro video game project. And we'll be picking up from where we left off last time, which is looking at the code for this retro video game at this point so far. If you haven't seen the first video, I'd suggest you go back and take a look at that, since we're starting from there, from the end of that video. So here you can see that the character in the white, the Ryu character, chases the Ken character, but he has some issues getting around on the obstacles, but it's not perfect. You can partially slide through like so. So it's not a perfect obstacle collision, but he does get stuck on the obstacles. And the Ken character in red also gets stuck on obstacles and also has that same imperfect collision detection. So this is where we're starting out with this program. In Python, we'll just run through the code like we did last time. So this is the shebang line where we decide which Python to run, interpreter to run this script. Then we import pygame and sys. We set a global variable. We initialize the pygame /SDL library. We generate a screen object. We set the title. We don't disable the mouse, so it's not visible. We load the sprites, which is the sprite. We load the SF back, which is this. You can see this little background, and this is how much of the screen we can see approximately when we first start. We also load this SF back mask, which just comes right here, which is the mask of the first one. We have our guy 0 and guy 1. We create their images, and we pull their images from the sprites by using an offset. We create the background, make it black, set the offset of the guys. They're both over to the left and either 150 or 100 pixels down. We created this move position collide with scene function, which takes a position, tries to move it in a direction. If it collides with the scene, doesn't move it at all. Otherwise it returns, and it returns the same position. Otherwise it returns the updated position with the X and Y added from the delta to the original, the change to the original. So then we have this while loop here, which is our game loop. And in this, we do this background blit. And as I said before, this is, I guess I could just cut it out. It's just a typo. My policy is every time I make a change to the code, test the code. Don't just make a change and save it. Don't worry about it. Alright, so here in the game loop, we have the guy 0 position. He's going to try to move towards the guy 1, and that's why we're saying if he's to the left of the guy 1, which is x and x, so if x is less than x, then move 1 over x. If it's greater than x, then move back -1 on x, which moves to the left. Previously moved to the right. This is the same here, except we move down, and here we move up. 1 to the y, -1 to the y. So that's the that will make the guy 0, which is the guy in white. He will move towards, but he won't be able to move things that he collides with. Then we check to see if we get any inputs that say quit, and we quit out. Otherwise, we collect the keys that were pressed into a dictionary, looking through the keyboard left, right, up, down keys. If the key is pressed, we move that way, left, right, up, down. And we use the same function that guy 0 pos uses, where we give our original position, we give what the change would be, 0 change on the x, 2 change positively on the y, and that will return either the same guy 1 position if there's a collision, otherwise it'll return guy 1 position plus that 0, 2. And over this, this is the size, and this is the scene mask, which is this that it's going to collide with. Finally, I added another little shortcut here that says if you press the escape key, exit out. So previously, you had to quit out by pressing that little button, and now I can quit out by just hitting the escape key, which is pretty standard thing to do. And I have to add it down here after I get the check keys, so this is in a different place. Finally, I render the background. I used to fill it with black. Now I don't do that anymore. I just blit is actually the same thing as draw. It comes from a blitter. I believe they called it a blitter in the Commodore 64 6502 terminology, and that carried over into the Amiga, and I don't know where else it came from, so I'd have to look that up to explain that any better. But anyway, we draw the scene at the top left, which is 0, 0. Draw the guy 0 at his position, guy 1 at his position. Finally, we render the screen, render, draw, blit, all the same. The background to the screen, again at the top left position, and we flip, bringing the back buffer to the front so that we can see it. And usually what happens is we toggle which memory is drawn from and which memory is now we're going to draw to. So one goes to the screen and one we use to draw next time. That's the way that memory system was set up. So that's the rundown here. The big differences between number 4, and this is the point of this particular series, the Get Off My Head series, which is this game. This series is initially going through these 20 files that I saved. So I'm going to compare 04 to 05 and so on as I go down. And in this case, what really happened was I added the move, pause, collide with the character that I move with the keyboard, where previously it had just been the character that moved with this very primitive seek behavior. So now we'll move on to Get Off My Head 6. And first, let's see how it plays. I actually haven't, I wrote this like 2 years ago, and I haven't really looked at it much since. I've been intending to do this project since then. So here we have, wow, it seems all kinds of broken. So I can move left and right. The Ken character, or the Ryu character in white, doesn't move at all. The Ken character can move left and right, can't move up and down. I seem to get stuck on this this piece right here. So this is a broken piece of code, but it's still the way that I saved it. I just went through stages. So every time I got to a new stage, I would save the code so that I would be able to explain it later on. So just because it's broken doesn't mean that this isn't a valid portion of this process. And so if we look at it, one thing I've done is I've started to move some stuff around. Here's why I can only move left and right, because I commented out the up and down. Here's why that's for his seek. Same thing here for my being able to move up and down. So that's why that doesn't work. And we find out together. And I put them in a different place. Previously they were at 0, 150, and then 0, 100. And now I put them at 300 and 360. So I might have actually stuck this guy move into that white space there. So he'd be inside this white space here, right there, and not able to move. So that could have just been a mistake on my part. But because I think he should still seek after me. So here you can see, we'll just do a rundown again. We have the shebang line, we have the imports, we have this global size variable, initialize Pygame and SDL, set the labels, all that stuff, load the sprites, load the background, load the mask, create the guy 0 sprite, the guy 1 sprite, background, the guy 0 in one position that's newly updated. So that's all the same. Then I created this new function called test collision by pixel step. And so let's read the description. Test for a collision against the scene, starting at start pause, ending at end pause, using step to increment. So that means this is where we would assume the position is initially. This is where we're going to end up. And so that means I've changed it from being a delta to being actually like you'd start at position 0, 0 and you'd move to position 10, 10. And so instead of having a delta change there for that, like a 10 plus 10, I'm just giving you the different position, giving this function the different positions. So it's slightly different from the way I did it last time. This is the step, which is an increment, which will determine how many times this occurs, or how many times we do a check. So it basically determines how much we slice this total space up into, and we're talking about the amounts instead of the number of times we're doing it. Scene optical color. The scene is probably the mask. I'll see once I scroll down there. Optical color is the white, so again, I'm using this white as the mask right there. And I put a log equals false, so obviously when I was writing this, I had some issues, and I put a log Boolean check there. So note I say here, note this function assumes that the bounding box has already been tested against the scene, and may call scene.getAt in negative or over scene size and crash. So essentially, the scene is an image. It's this image right here. And if you try to get a pixel value, which is that getAt function, it tells you the pixel that's there, and you try to get it here, or off the side of the screen here, or off the side of the screen here, you get a failure, and in a lot of libraries that will just crash. Some handle it well, some don't handle it well. And then depending on the code you expected, you may get an exception thrown, or you may get like a none value or null value, nil value, depending on your language. And so it depends whether they do an exception where they basically change the execution stack on what's going to run next to handle the exception, or maybe quit out of the program if there's no default handler, or you get a new value. And if you get a value you weren't expecting, you're expecting a sequence of RGB values, but what you got was a none or nil value, then your program could crash there as well because it's not expecting that type. If you don't have that static typing. So I'm just letting you know this is an unsafe function. That's what this is saying. Already test the bounding box before you enter this function. So here I have, we create deltas of differences for the step in X and Y, depending on the step. So this is essentially giving us a direction. We're either equal, which means dx is 0. We're greater than, which means we need to go to the left, which is negative. We're less than, which means we need to go to the right, which is positive. And this is the same thing with y. We need to go down, we need to go up, we stay in one place. And then I say basically, if you're not going anywhere, here I have this colorful exception. What the fuck, the start and end positions are the same, handle this case later. Obviously I wrote this code with a friend and not for a business. So determine the distance required to travel in X and Y directions based on the start. So this gives us the total distance in X and Y. Here we're recreating the current position because this is going to change. Why do this? This was actually a little bit of future proofing if I wanted to add a third dimension. And there's a couple ways to add third dimensions. You can have a full normal third dimension where X, Y, and Z all have their own infinite axes. Or I could actually just have like an indexed offset Z dimension or third dimension where I just have kind of like -1 and +1, and they're just kind of like right next to each other. And there's not like a full infinite axis for Z. So in doing this, instead of just doing a list, I now know that I only have 2 elements. And so if there was a third element, I wouldn't get a list of 3 elements. I'd only get a list of 2 elements, which means then I can really know that because this is a 2D function, that this is only going to be a 2 element. So that's what this is. This is a little bit of future proofing in case I want to add a third dimension at some point in this code. And I'll end up doing that a lot because it doesn't cost me very much. I would have done the same thing. The same number of lines would have been taken up if I just did this. And I could have also done this. That would have also worked. So either one of these would work, but I think this one was the most expressive to me. And when I write code, in a lot of ways, I'm writing messages to myself in the future because I'm going to come back and work on that. And this is one of the differences between programming on your own and programming in a team environment. Is in a team environment, that needs to be documented more, why this is like this. Whereas in this environment, I can look at it and just intuitively figure out that's what I was trying to do. So loop until we reach the end of the position or find the collision. So we're going to set a bunch of default values, which we'll then probably try to modify in this loop. So end position's been reached. Nope. Has a collision. Nope. Distance traveled 0. So obviously we're going to work towards the place that we're going to go. That's that distance traveled. If we hit a collision, we have to stop working, and then the end position reached is also not true. We haven't made it to the destination. So while not end position true and while not has collision. So while we haven't reached the end or hit a collision, we're going to do this whole loop right here. And so if you notice at the end here, all we're going to say at the end is whether we have a collision or not. If returns has collision, it's just a true or false. So that's why this function is called test collision by pixel step. Now, one thing you notice we don't return here is we don't return when it had a collision. So this is a kind of simple function at this point, in that it tells you that you do have a collision, but it doesn't tell you when you have the collision. So all I can do is react to this in a Boolean fashion because this is a Boolean value, and that's all we respond with. Whereas if I actually gave you the position that we stopped, that would be much more interesting. In fact, even more interesting would be whether we collided and what the position was, so that in the calling code to this function, I don't have to do a test to see if the position and the original end target were the same. So even in the writing of this function, this kind of investigation that I'm doing on it, where I look between 05 and 06 code and I compare them, I can see the progression of how I first created this function, and then as we get into the later versions, I'll be modifying this as I realized that, like, while I got the initial thing I wanted, I didn't get later things I want. And there's a balance between trying to get everything you want up front and just trying to get something that works and allows you to take one more step. Both of those things are important, but the only one that will get you to a finished program is the one that takes you one step further. If you try to shoot for everything all at once, all the time, then you'll always be working on features that are not going to finish the program, and at some point you have to finish the program. So this will be part of the lessons of this programming with layers of abstraction, because the idea is you're building up these layers of not only abstraction in programming, but abstraction in your working ability and workflow. So if you can't realize that always looking at the big picture will never finish the project, it's because, they call it like featureitis, feature creep. There's, lots of words for when you keep adding things. But if you're always looking at the big picture, you can usually come up with either ways to rebalance things or new features that should be there. Whereas if you're only taking one step further, the idea is that you've always got an end goal, like you want to drive to a certain location, and every time you get onto a road, maybe you get lost, or maybe you go to a road that wasn't like directly towards that goal, but every time you recheck, you look at what roads will get you closest to that goal, and then you take that road instead. Maybe you'll have to backtrack, and then you'll go in there, and that's the same concept that taking one step towards the goal is, versus looking at the total picture of everything you might want. So you need to balance them, but it needs to be leaning towards stepping towards things so that you can actually finish your programs. So anyway, we do this test thing. In the loop, this is the while loop of while it hasn't reached the end or a collision. We get the scene value. And so what this is the scene, which is undoubtedly going to be this this mask. We get that value at the current position, and we take only the first three. Now again, this has to do with the fact that there could be 3 or there could be 4. So it's RGBA in this picture, the A being the alpha or opacity channel or byte value. So taking the first 3, we'll get R, G, and B, the red, green, and blue, and this allows us to test against this, which is R, G, and B, red, green, and blue. So red all the way, green all the way, blue all the way makes white, because that's how it works in light-based color theory. So we get this position, we get this RGB value, and we know that this is going to be no more than 3, and because of the system, it is actually going to always be 3. The library would be broken if it wasn't. So I've made some assumptions here, but that's how programming in this language works. So then you can see I have this Boolean log. So I say if log, and right now I say log equals false. Then print out the color, or print out the dx, that's the delta x, the delta y, the start position, the current end position, the current position, the distance we traveled in x, the distance we traveled in y, and finally the pixel, and that is the scene value. And so you can see I'm just doing a printout of what's going on. So I would see that scrolling by, and I could look at it and do debugging and test whether I'm actually testing in the right place. And this is there's a couple different ways to do debugging statements, but this one is a very printing things out to the console screen, just like we did in the last series video, which did this, printing out whether the top left, there's the pixel coordinates, here's top left, TL, bottom right, bottom left, top right, and then we see in this pixel coordinate, this is white, and in this bottom left one, in this pixel coordinate, it's black, and it just keeps going, and that's how we're testing whether there's a collision or not. And so this is the same thing, only it's giving me more information, and I probably tried to tune that so it stays in one line when it just scrolls by. And then I can look at that information as I'm playing the game, or stop someplace, or even quit the game, and look at what the state was right before I quit, depending on how I want to do it, and then I can read these values, and that will help me in debugging. So this allows me to use the program while it's running, looking at the values. And there's other ways of doing this, like instead of just using a text editor here, I could be using an integrated development environment, IDE, or I could be using just a Python debugger from a command line interactive program. And both of those provide you a way to run the program and then stop and inspect values and inspect code at certain points. But they don't work in such a way that you can look at it while you're using it. So both of these are useful. Sometimes that's usually I look at for kind of deeper bugs, like if I have a bug I can't find, using this method. And this method I use so that I'm just getting feedback from the program. And also at a certain point in the program, you can print it out on the screen itself in the game if you have that kind of a thing, or you can put it into the web page as like a pop-up or some kind of hidden element, or like an alert that goes off if you hit a certain key combination that's your test key combination. So that's what's going on in there. That's why I have this log line and the way I use it, and you'll see me do it as we go down through this. But it's a good thing to think about this process of how you'll get feedback from your program, find out what your program is doing, so that you can go back in with a head full of information about what your program was doing at that time, and then you can fill in the state as you look at the variables that you've created, and the function calls you make and things like that. So anyway, we've got the scene value. We've just started this while loop. We've got the scene value. We printed out a log if that was set to be true, which it's not by default. We test if the scene value equals the scene optical color, which is this white color here, RGB all 255s. And if it is the same color, we set has collision is equal to true, and then that will finish this if block. This else block connects to that if block. And there's nothing else going on here. So then we'll return to this while loop statement here. And it says, while not end position is reached, so while we haven't reached this end position, and not has collision, so we don't have a collision, but we do have a collision. So it's only going to do this block while we don't have a collision and we haven't reached the end position, but that just became not true. And so now we'll jump all the way down here and we'll return has a collision to whoever called us, and then that will now be true in our current test here where we said it was. And that's it. That's this function in that case. Now, if it's not true, what happens is more interesting, right? Because this could happen on the first time. If you're currently colliding with something, you've got a collision, end of story. So, if it is not true, we're going to work in just this else block right here. So all this else code is all one thing. So this is going to be the majority of where this while loop happens as we're checking for distance, looking for collisions, or looking if we reach the end position. So first thing we're going to do is we're going to redetermine our current position after we add the dx, which is the direction. It's either left or right. We're moving one step at a time. So either 1 steps or 0 steps. That's what this delta x, delta y was about. And so I'm going to do delta x multiplied by step. So I actually got it wrong when I first described this. Step is going to be the size that it goes, and dx is going to be the direction. And so if step is 0.1, then dx will be 0.1 to the right, and it will move it 0.1 pixels over to the right. And then you see we add that to the x position here of the current position. So the current position is 1 step closer, 0.1 closer, if we're going to the right. And it's the same thing for if we're going up or down, negative 0.1 or positive 0.1 if step is 0.1. If it's 1 or if it's 5, we go 5 to the right, 5 to the left. So that's essentially, this is our velocity here. So this is our velocity times our direction, and we just have these two kind of nearly Boolean directions of either right or left or nothing, or up or down or nothing. So we just have velocity times change in direction added to the current position equals the new position. Then I also do distance traveled, which started here at 0. Now each time we loop through this while loop, distance travel will be incremented by the step, which is the velocity. So we've moved that far. So then I do a test. And you can see this is the entire test block. So it's either going to do one of these things or the other of these things. So if the distance x does not equal 0, so it's moving forward, and it's not... so what I could have done is I could have actually tested if dx is not equal 0, because that means we're either moving to the right or the left. But instead, because I knew that the distance x where I set that? So this is the distance x. It's the distance of x. So instead of doing it with this method of the direction, I've instead done it with this method, which is how much there needs to move. So if we need to move, this is what this block says right here. And this block says the same thing for y. So if we need to move to the x at all, either the left or the right, and the distance traveled, which we just incremented here with our step/velocity, is greater than distance x, then the end position is true. So we have moved all the way we needed to move to get to the distance traveled is equal to or more than the distance we needed to get to x. And if you notice, this has an absolute value associated with it. So even if it's going to the left, which is negative, if it was negative 10, it still shows up as 10. So that's how much distance we need to move. And that we know that this will always increment up. So because it's always positive with the absolute value, negative or positive is positive, then we know that if we're only adding acceleration to this, which is only going to be positive, we won't have negative acceleration. Negative acceleration would actually be positive acceleration in the opposite direction. So if we know we're going to move on X, and we have moved at least as much as we need to move, we can say that we've reached the end position. And then what we can do is we can use that end position that we already knew about. We, in fact, passed it in, I believe, as an argument. Yep, there it is. We passed it in. If we look at the end position and we get the scene value for that to look at the final destination, we can determine... this again. So this is for X. So we can determine from that final position in the end pause, if the scene value is the opposite color, then we have a collision. So even when we get to the very end, we do a test to see if there's a collision, to see if you're at the very end. But you still made it to the end. So this returns true, and then this is for X. And the reason this is if and else if is that either one of these things could be true, and we know we're done. Also, that means that what I'm doing is you can't move X and Y at the same time here because of that else if. So again, I wrote this a long time ago. So the inputs here are either going to be to the left or right, up or down, but not left and up and not down and right. So this is a specific function, and I didn't put this in the note here. But I can tell by looking at this code, because if this is handling X and this is handling Y, then no case is handling both X and Y, because this is if and else if, and not if and if. If they were both ifs, and then they took into account the merged X and Y values, that would be different. So, and I will show you now that I remember it when we get down to the bottom. So again, this just determines if it has a collision, but it will stop working at the end position on X, and the reason is while not end position reached. So it will not do this any more of these iterations. And this down here does the same thing for Y. We just say if we're moving in Y, that means we're not moving in X, and the distance we've traveled is equal to or greater to the distance that we needed to travel, then we've reached the end position, get the scene value, determine if we had a collision at the final position, and then finally we'll be done with all the paths of this code, and then we return with has collision. And what I just did here, breaking down this function and going over every path of the code, is pretty much essential to being able to create quality code where you haven't baked in errors because you didn't really look at it and you didn't run through, well, what if it's in this case? What if it's in that case? Whereas if you run through every single case and you look at what values could be in there and you determine, just like this, could this scene value ever be 4? And then I'm comparing 4 values with 3 values, which will never be the same because a sequence of 4 values and a sequence of 3 values can never equal the same thing. But because I use this slice here, this sequence slice, which says take from the beginning to the third element, which is actually the fourth element because you start counting and computing at 0. So take from the 0th element to the 3rd element, the 3 index position. It's a little confusing to talk about this stuff sometimes. This is the 4th position. So from the 1st position to the 4th position, grab the first 3 positions. And so I know this is always going to be 3. And so I know that as long as people pass in 3 values here, which I default, then I can make a valid comparison with this equals. So it's like knowing those input values is key. If you're getting any input from the user, you have to spend quite a bit of effort to make sure that you evaluate the input they give you, and you know that they can't give you bad values. And that way, and that as from files or getting things from any kind of source that isn't your own code, and then in your own code you have to decide how much protection you need inside your code from doing those versus assumption that because if someone broke it by making a change, you would find it by using it. So that's a different kind of test. And you'll also notice in this project I'm not using any unit tests or anything like that because it's an interactive video game and it's made for demonstration and it's not made for a team business project. So this is strictly about how to program and the complexity of programming and how to manage the complexity of programming, and not about how to work on a team in a business environment in a way that's friendly to the team and the lifecycle management of a company. So these are different things, different skills being worked on here. Now in the move, position, collide with scene, the previous function that we had here, one thing you can do if you want to see if things have changed is you can line stuff up and just move back and forth. So here you can see I added a log false line in 06 that I didn't have in 05. So I got this logging idea when I created the other one, or maybe in between. Who knows how I wrote it. And I added this this value here, right here, log equals false. I didn't change the doc string here. So I didn't change the documentation, so that means that the function probably hasn't changed too much. But then you can see down here, some other stuff has changed. There's flickering that's going on down here at the bottom, and that means that stuff changed too. And the big one I see is that I set this step test equals 1, which is probably going to be something we call. So this is the same. Has collisions false. This is going to be the target position. Here I test to see if you go outside of the scene. And if you do go outside the scene, I immediately say it's a collision. I don't let you walk off the scene anymore, like I used to in previous versions. Here I say if it hasn't had a collision yet, then we're going to do a step test. And the step test is going to go by 1 pixel. And then we're going to determine the corners, top left, top right, bottom left, bottom right, like we did before. Obviously, I haven't put this log line in. I just put the infrastructure in for that flag. So I must have got the idea from the previous function and then put it in here. And if you notice, there's a little bit of forensic investigation that you can do here. Like, how do I know that I put the other one in first? I know that because I put it in here, this log equals false. And then I actually used it. Here it is right here, if log, printed out. And then what I must have done was said, well, that was a good idea. I should do that here too. So I put logging false here in the arguments. I even forgot to add it to the argument list here. And then I went back and I put it in here, but I didn't make it print anything. I just put this in as a placeholder. So this is all just a placeholder. It's a note to myself that this work needs to get done. And I just put in the structure of the work without putting in the content of it. And so just by looking at this and looking at the fact that it showed up here, I can tell using essentially like forensic detective methods which came first. And without even having to look back to this, this one's filled out and the other one's not. So in all places of code, you can actually see this stuff if you pay attention to it. And I really recommend that you do, because you can find this in other people's code too when you look at it. And that will tell you a lot more about the progression of the code. And if you look at a full environment of the code and the directories and the files, you really get to start to see which thing came first. And it's kind of like archaeology, where you're basically unraveling layers of dirt to find, oh, here's a pot. Oh, here's some bronze stuff. So pay attention to that. It's interesting. That's another skill to build up. Anyway, back to the code. Here we test the bounding box using, I say, an n pixels to get a better resolution on obstacle collision. So I'm trying to improve the obstacle collision here by using the step method. And so here I call that previous function test collision by pixel step. I give it the top left corner, which we assigned above. I give it the top right corner. And then I do a step test. And so what that means is I'm actually going to go from the top left to the top right and move by that step test, which is 1. So I'm going to move 1 pixel every single time from the left over to the right. and that is going to look for collisions all the way along that edge. And finally, we pass in the scene image, which again is going to be this mask, and I pass in a log that says whether to log. So even though I'm not using any log here, I'm just printing out a new line, I'm still collecting this value, log here, and I'm passing it through to this function. So I both log on this function, and I log on this function up here with this. And so there's a chained effect. So if I say to log at all, then I get logging all the way through. And that was another reason to put this in. So not only was this a placeholder for where I could log here, but it was also a pass-through mechanism. So I only specify log once, and then I can turn it on and off, which is good. So then I set has collision is true if this evaluates to be true. And I have to do this all 4 times because you see I'm testing from the top left corner to the bottom left corner, from the top right corner to the bottom right corner, from the bottom left corner to the bottom right corner. So I'm tracing all the way around the box of the sprite. So I'm only getting the edges of the box of the sprite, not the actual edges of the sprite itself. But that's still much better than it was before, because before I was only testing the corners and not all the space in between the corners, and that's why you could do things like move right over some of the obstacles if you aligned it in such a way that the corners didn't collide. So here you can see I just did a copy and paste here of this with this, and I define again the top, left, bottom, and right. It's different here because I'm using this bounding box size. So here I'm starting this is interesting. I did it the same way in 5 as I've done it in 6, but I had this other method here. This is the scene top, left, right, and bottom. This is what I used to do here. Okay. Yeah, I misread that. My mistake. So the scene, I've commented this out because I don't need to test the scene in this anymore like I used to, because now I test every pixel along every edge of the image, and previously I only tested the corners themselves. And then I just did a test against this. So here I've just commented it out, but I've left it here. So now I have 2 different versions here, and I can flip this back. I could comment this one back, like so, and then this one could be the one that gets done, and that's why I left it there. Now, when you work on a team, people don't like it when you leave code like this in here. But when I work on my own, often I'll want to leave this in for at least one check-in, always at least one check-in, and which kind of bothers me about some teamwork is that when you lose this historical information. You can't go back and get it. But if I make one check-in that has this commented out, and then I delete it, and then the next check-in I put in this, it's like there's a progression. It's a 1-2 step. Here is what I changed, and you can see the differences of it, and then I put in the good one. But in a lot of companies, they don't like to have that because they don't like any check-ins to go in with all of these commented out code. So they're losing that historical data by doing that. But luckily, when you're working on your own projects, you can do it your own way and come up with your own conventions, and you should do that. You should figure out the best way you can possibly program, and then when you work with other people, you have to comply with the conventions that allow that teamwork to happen. But if you don't try to be the best programmer you can be on your own, when you write your own software and coming up with your own methods for how to do this, then you won't get any of those advantages. Finally, it comes down here and it says has collision, if has collision, and then basically we don't move again, and then otherwise we move to the target position. So once again, we haven't changed the fact that we're either not going to move because we've collided, or we would collide, or we're going to move to the final place, and there's nothing in between. We don't move a fraction of that to get right up next to the barrier. We just said if we would have moved into the barrier at our current acceleration, then stop, which may leave a gap. Finally, that ends this function here. So now we've got the updated move function, and we come back here, This is the game loop. We blit these guys, which again was a mistake. I don't need it. I left it in there for far too long, just not paying attention to it, I guess. And like I said, make changes, test the change, even though I tested it before. This is the while loop block. Here I only move the X position left and right. Here with the keyboard I only move the X position left and right. Standard exit pump, standard escape key, exit, render the scene, render guy 0, render guy 1, flip the background, flip the display, and that's what we got. That's the updated version from 05 to 06. So let's see what we get with 07. Alright, the movement's back on again. So probably one of the big things is I uncommented out the stuff that I commented before. Now also, if you notice, I'm always kind of moving down. He's always kind of moving down. It looks like I added gravity. So not only do we both do these pixel tests, and now if you look, I don't go through the object. Here I can't go through the object again. I can just raise myself up by pressing up. It's not like a jump. He doesn't do that though. If you see, he won't jump up for me or move up for me, but I can do it. But we both have this downward thing that's happening over time, which is essentially gravity. And if you notice, I couldn't have added gravity before because it would have constantly pulled me down onto these barriers. Like I could stop myself this way, and this is interesting. Here we can see that I'm over here, I slide down, but then those extra pixels that catch me. So now I'm essentially standing on that little edge, and gravity will just keep pushing me down there. And if I fall down here, I should go right through that stuff and then hit the very bottom of the screen where it's like it doesn't want to let me go down. And you see that extra couple of pixels down here, right here? This is the difference of me being able to move partially to the collision point rather than having to stop before I've done my movement. So it's like it leaves those pixels there beneath my character because it's not colliding with white, it's colliding with an out-of-screen area. And that I won't let it do that test because, again, I said in the note that it wouldn't work. So if I allowed moving just like 1 pixel instead of like 2 pixels like I told gravity maybe to bring me down, then it would allow me to move right down onto the bottom here and you wouldn't be able to see anything underneath him. So you see the same thing here with the white character, which is that there's a gap underneath between where the actual white would be, assuming that I didn't draw it incorrectly, right? I could have drawn it higher than this actual color is. But there's still a pretty big gap there, which means that the downward force isn't taking him as far down as it could be to sit right on top of that white obstacle pixel. And that's because of the very primitive collision detection that I'm doing right now. So I can hit escape and quit out. And let's go take a look. We've got the shebang line, the imports, the global size setting, SDL and Pygame, and the title and the mouse. We've got loading the sprites. We've got background scene, the mask. We set up the first guy's image. We set up the second guy's image, 0 and 1. Background, it's black. There's the positions. Notice I've adjusted these a little bit more because I might have actually put them into the obstacle last time, which is why they couldn't move left and right. In fact, I'm guessing that's true. I have this test pixel collision step by step. So we'll do the little test again here, just to make sure I didn't change anything. And it looks like I didn't change anything. And what you do is once you test it on one page, you kind of have to page down if you want to use this flip test. Now I could just diff these things as well, which I'll show you in a second. So here, no change. Then I go down to this pixel collision true and pixel collision true, and over those 2.1 pages of code, I could see that there wasn't a change. And that's good. And I can even do the same thing here with this. So now I've tested this and come back up. And which one was it? Yep, the to do right here. No change here. Come up to say this and this. No change here. Now in this true section, while true, this is in the game loop. Here we can see there are some changes. For instance, get rid of that again. I won't test it this time because no, it's true. So the old one, the Y positions were commented out. In the new one, interesting. So in the new one, it's only got fall for the guy. So he won't go up anymore or down anymore to track me. He'll only fall. That's why he just fell to the ground, and then he moved X and Y. So when we look at this, the white character, he follows me when he can, but he can't go up. But if he gets to a place where he can fall again, he'll fall and still follow me, but he can only go down. He can no longer go up again. I can press up because I've still given myself that ability, but he can't. So he lost his ability to track this. And then he'll only fall. So then I do the quit test, get the keys. I do my left, right, up, and notice I've commented out down. So I can't press down anymore. When I press down, it doesn't actually do anything. I don't accelerate my downward motion. That I'm pressing it right now over and over again. It's not doing anything because I've supplanted pressing down with gravity. So I can press up, and if you notice, I usually move by 2, and here I move by 3, and the reason why is that I'm constantly falling down by 1. So even when I move down by 3, gravity, or I move up by 3, gravity will bring me back down by 1, and essentially I'll be moving 1 down all the time. So I'm also falling. And if you notice, every one of these uses move, pause, collide with scene for the behavioral kind of AI character, NPC character. That's the non-interactive character, non-playing character. And for the playing character, the one that I control as well. If you notice, I never put the log in over here. Log is true. So one way to do that without having to edit this code, if I want to test it, is I just do this. I just make log is true there as the default, and that'll fall through, and then I don't have to edit all this code, because that's a pain. I could even put it as a global variable where I have something up at the top that says do log equals true or false, and then I and then I comment this one out, and then I change this to do log like that, and then I could just flip them like that, and this would actually be at the top with the other global variables, but I can just flip them like this, and this will also change whether log is true or false, and that could work for everyone. Every function could have that same effect, but this is because I'm just this one chain. I could also just change it there. So that's how you can kind of affect downstream logging, since if this one logs, then this one will log too, because we pass it through. So anyway, that's it. We have gravity now, and we can kind of go upwards against gravity, but the other guy can't. Let's find out what the next one is. So now I've added a primitive jump function. So the other guy can't jump, but I can jump. And if you can see it, this is where the game is going to get its name. People jumping on each other's heads. That's where the get off my head theme comes from. And now it's actually starting to be a little more of an interactive game than it used to be before. And so if you notice, because the scene is actually bigger than the screen shows it, I can actually run off to the side here and come back. There's nothing wrong with that. But it won't let me do the same thing over here. I haven't tested it in a while, but because of that border line that I put in where I don't allow testing outside the bounding box and the scene, it won't let me go to the left, but it will let me go to the right. And there's still no collision detection between the characters because we haven't added that yet. So this is what we'll work on next, now that we've added in a little bit faster of gravity, and it looks like it might even have some acceleration to it. Let's test. Yep. hard to get that working. Yeah, it looks like there might even be a little acceleration of the gravity, and then maybe with a maximum, and then there's definitely a jump, and my character can jump, but his character can't. So that's where we're leaving off for now, and then we'll come back in the next part of the series, and I'll keep going through these first 20 saved pieces of code that I did one night 2 years ago, and then we'll start taking it further with some new features, and I'll do some live programming and explain both the plan on how to take it further, how to build the plan of how to take it further, and then finally do it and show how I do it to wrap this into a fully functioning game that can be released and people can play. Not that it's actually kind of fun. I'll do one more thing, and I'll show you what this looks like in its current form. It looks like this. There's a little health bar up to the right. It's a little sluggish right now, but there's a bunch of these characters jumping, and if you notice, I can stand on this guy's head, and oh, got him. So if I stand on his head long enough, I'll take his health, and then he disappears, and he reappears later on, like someplace else. So here I'm jumping, and trying to avoid them jumping on my head. I've gotten a bunch of people. So notice there's no score yet, and I don't have any lives, but if someone stands on my head, then they bump me down. Also, you can notice the characters bounce into each other. So this is what we're working towards. This is what the game 20 save is like from where we've been. So it's almost a little game. There's definitely some gameplay or some play. There just aren't any starting and beginning points, and there aren't any score or other kind of measurements of success. So with no beginning and no end and no measurement of success, it's not a true game, but it is some play, and it actually has a little bit of fun moving it around. The only problem right now is it's too slow, so we'll do some performance tuning as well, which should be interesting. So that's it. This is the end of the second video, and we'll have the third video up pretty soon, and we can see what's coming next. Thanks.